Good morning, good evening, and good afternoon. So I'm happy to see you all virtually. And today we will speak a little bit about some kind of machine learning stuff. And give me a few seconds. I will prepare my presentation as well. Here we go. So today I will speak about YOLO family and how it goes, and we will a little bit investigate the family business, how it goes and why and so on and so forth. But who am I? I'm Rinat Akhmetov, and I'm ML solution architect for Provectus for last several years. And basically I'm working with some kind of object detection, computer vision, tracking, so on and so forth, this kind of models. And therefore, when the new article came out with the weights, and we just did a best effort to apply it as soon as possible. So YOLO began to gain popularity, and people used and come up with a few articles in the year. For example, right now we have a 2.6 version and 2.7 versions, but we will pay attention only the ones that inherited from original. And yeah, as you know, as a Saul Goodman, the author of original YOLO would like to be a good man, and for ethical reasons stop working on CV model, and therefore it was inherited by Alexei Bachkovsky. Sorry if I just mispronounced his name, but yeah. So we would like to start, and what we will discuss today. We will discuss a little bit about what is YOLO, and how YOLO v7 looks like, what the back of Freebies was invented in this article, what applied as well, and also we will understand what kind of YOLO exactly we should use for particular reasons, and compare a little bit this YOLO with others, and understand in which area it could be better or worse than others, and just go through a little bit application of these YOLOs and how we do inference of this YOLO in our company. So here we go. And I would like to pay your attention on three main parts of this YOLO and object detection models. First of all, I would like to say that there is a backbone, neck, and dens or head. So backbones is no more than just extracting features for particular images, and you see it as a pyramid on the left side. It's from extracting features from with a different strides from these images, and then all these images from different levels of this pyramid come to the neck. That it's mix it up, trying to come up with new ideas from these features and provide all this information to the head. So head, because of this head, it's working especially with detections, bounding boxes, as well as labels, and do it in a one stage. It named like one stage detector. Especially all this YOLO family dedicate entirely purposes to increase the speed and with a good enough performance. And all these modifications has been applied in this article is made specifically for increasing performance on particular devices, but latest technology applied. So as far as I understand, there are different YOLOs, and all of them could be aligned in the following way. So there was a YOLO v3 that was adopted and maintained by Alexei Bachkovsky. Then he invented YOLO v4. Together with a few more guys, they applied a new scaled YOLO v4. Then YOLO R, that's not actually YOLO by the name, but you're wondering why it says YOLO only. But no, every other YOLOs, it says you look only once on the image, whereas YOLO R, it says you need to learn only representation. So the different name, the different purposes. But in this article, they applied all previous knowledge that has been made and come up with a new idea that helps them to improve the accuracy, decrease the amount of weights, and push this frontier even further. Here we go. And right now we will speak about how this model especially looks like. I mean, the YOLO model. It, as I mentioned before, we have a backbones that's labeled like blue ones, and this one this figure, and we also have a neck that's represented with a slightly red color. It's mixing up all of this information that's come from the image and push it to the head that's just actually made a decision. Pretty simple, huh? And we can go a little bit further and understand that this when we look at there's a picture on the article, we see we have a YOLO v7 tiny, YOLO v7, YOLO v7x, v6, d6, and e6 and e6e, and you just could wonder why so many YOLOs in the same paper, and how we can which of them we should apply and how they differentiate between each other. We will pay this thing a little bit attention later, but right now I just would like to emphasize that the basic YOLOs, like represented as these small YOLOs, they're working with only these 5 stages. Each of these stages represent the power of 2, how close all this feature has been extracted from the particular image. So this is a number of layers of this pyramid. And there are also big brothers. It's YOLO, big YOLOs, and they can see 6 stages and even more. But if you understand that's bigger stages, bigger model, and it could be run only not just edge devices, but for cloud GPUs as well. So and I will pay attention on all this particular stuff a little bit later as well. Thank you, and here we go. We ready to start from back of Freebies. So what has been invented in this article, or even applied from different papers? So basically, we work with model reparameterization, batch normalization, and coarse and auxiliary affine lead loss that's been applied for this article, and few more stuff like implicit knowledge from YOLO R. It actually YOLO R had that came from previous paper, but it cooked in a well done in this article. Also AMA, it's exponential model average. So here we go, ready to start from some kind of math, I guess. I hope in it. But anyway, so just would like to remind you what is identity connection. We have a few layers of neurons, and they work with each other, and you're just seeing one convolution layer, then activation function, another convolution layer, and and you can do it how much we want. But to be able to train the model, you need to make gradient path a little bit shorter than that. Therefore, this made it this kind of keep identity connections. And so right now we just understand that identity connection is just avoiding a few steps and make a back propagation a little bit shorter. Here we go. And right now, what has been come up in this article? They say, okay, we have a lot of memory spent wastely, I don't know. And what if we will apply a new approach for decreasing the amount of memory? How it works? So when you working with all these feature vectors in a memory, it will require all. So for example, you're working with convolution 3 to 3 and 1 to 1, and also batch normalizations, so on and so forth. All this information will be kept in a memory, while it wouldn't be concatenated or edited in a some merging and union point. And there is a technique that could little bit decrease the amount of memory that's used. That's named a plain net, a simple net, that's you seeing on the right side. And to get this idea, they say, okay, we just need to completely avoid all these extra layers. But they are required for the training, you say. Okay, therefore, this new model, name it like rep convolution, is using a one-to-one convolution and identity connection in the middle during training, but completely avoided in an inference stage. And you can wonder why, how it works. But I will not go deeper to the math. Let me simplify a little bit. It just reduce all this convolution by mapping all of them into 3-to-3 convolution layer for this batch normalization especially, and then it just summarize all of them into one convolution 3-to-3. Therefore, you can keep all this information that's gathered from batch normalization, from convolution layer, one-to-one, so on and so forth, into one convolution layer. So you're saying you can wonder how it works, but they empirically understand. So I just emphasize that it works in the article and it works well. So, and but it doesn't, if you will apply all this technique, especially for ResNet, on darknet, or densenet, without any modification, you will get an error because it may completely destroy all information that's come in during training stage. So let's go through, all this figure chart that we're seeing right now. We see a plain net on the left side and ResNet on the right side. And what authors of this article came up in this, they came up with the idea that if you just use all this rep convolution layer as is with identity connection, it will completely broke for backpropagation techniques that came up with ResNet. Therefore, they say, okay, when we're seeing identity connection, for example, on the right side, we just need to remove identity connection from previous layer. So let me make it clear a little bit. Rep convolution itself has its own identity connection, and we have an identity connection between two different blocks. And author says, okay, if we have two identity connections in the same time, this came from different levels, it may, it doesn't help to the model to train, and we can just avoid identity connection for rep convolution layer, and it will works even better. And therefore, this came up with rep convolution N. That's avoid an identity connection, but it works only for the places where we have two identity connections at the same time. Here we go. So these two things just offers to decrease the amount of weights that's used for the model, and also increase performance, flops, and everything. So far beyond that we have right now. And they applied all the stuff, just different techniques that we're seeing on these figures, and all these experiments was proved that idea works. Yeah, so a little bit strange. It's presented in the article and was accepted, and yeah, definitely should work better than that. So we can move a little bit further, and I mentioned a batch normalization. It's the same idea. Idea is the same because we just, merge all this batch normalization activations into convolution layer and decrease number of weights and increase the speed of flowing during inference stage. Wonderful. But what about a little bit boring stuff? Should we listen to it and understand how it works under the hood? So we have a formula that can be simplified and understand what's going on over there, but it's a little bit boring and just express it a little bit previously. I guess you haven't understand it. The same thing the authors of the article applied for YOLO had. There is some such stuff like implicit knowledge, and it was applied from a previous paper. However, they added the same, they just merge everything inside of in inference stage. That helps them make it even faster than it was before. So a lot of stuff has been done, and few more things left. I mean, there is an xiliary head. So yeah, here authors explain a little bit difficultly for me, but there are lead head or the teacher and auxiliary head as student. And eventually we would like to, pay attention of lead head or teacher on some sophisticated and comprehensive stuff, whereas students should pay attention for investigating new techniques and new stuff around that. And then lead head or teacher will comprehend with some new ideas in this kind of article. So auxiliary head is pretty common, popular thing, and was applied for training YOLO models. It works only for models that has a lot of different features that comprehend with all this idea. So, but it couldn't work as is, because if you just provide equal heads that can make a prediction on the same ideas with the same target, it couldn't work, because in some time can happen that a student will understand or provide the same information that the teacher is. Therefore, they're saying, okay, student should pay attention for more stuff than teacher, and they made it by a Coarse-to-fine label. It's how it works. It works in the following way. So, for example, the ground truth data, it's represented in a pink color on the left side, and this is the ground truth for the teacher. And for example, I need to emphasize that we, for example, resolving problem of segmentation, and we segment all this pinky cells in these boxes. However, students should pay attention more than these three boxes to let teacher to understand what kind of information are vital or not, and comprehend with some sophisticated information between all these layers. And all this name it like Coarse-to-fine lead head guided label assigner. And of course, it was proved by different experiments has been applied in this article. Of course, the method that they proposed, it's the best one, and it provides even a little bit push forward in terms of average precision. And here we go with the latest idea. So there was ResNet XT. This is XT. This is a model that invented in 2017. And they proposed to use some kind of groups of convolutional layers inside of your network, and it's saying, okay, you should pay attention on resolution. It's the size of input image, the number of layers or depth, and the size of feature maps or width of this number of channels. And also you can pay attention on stages as well. This is a number of this component blocks inside of it. So, and I mentioned 4 of them. 3 of them was applied in EfficientNet paper. It says width, depth, and resolution as well. Whereas stages, amount of this block was applied in scaled YOLO v4. So I wouldn't like to I wouldn't like to pay more attention on this stuff, but I just would like to emphasize that the author of this article would like to say, okay, you can make the same thing, apply ResNet XT architecture for our YOLO models and our backbones, and it will increase the amount of, you can increase the width and amount of blocks of YOLO, and it will be able to work with the different data. How it works? For example, you're working with a small images like 640 to 640, and you need just maybe few blocks. But in the same time, you would like to increase the amount of blocks and work with the bigger pictures and find a pretty small and big objects on these images. For example, onto Full HD or even 4K photos. So you need to increase the amount of this kind of blocks, And this is how actually the authors invented all these different YOLOs. So I would say there is a YOLO v7 tiny, then they added a few component scaling blocks and get a YOLO v7, added a few more and came up with a YOLO v7x. The same thing was made for v6, d6 and e6 as well. So they differentiate by amount of blocks that's been applied for this model. Here we go. And everything was, they absolutely right. Provided proofs for all this stuff. So if you would like to work with this only, def only, or just only, so it wouldn't help. But if you just compound all the stuff, which is actually good, will work fine. So, and the last one, invention, as this thing, they presented a ELAN. So it's a little bit complicated, but let's make it simple. They're saying, okay, how to design an efficient network. They came out with the conclusion by controlling the longest, shortest gradient. Then a deeper network and could converge all this efficiently. And this paper just came out with a proposed extended ELAN, but how it looks like. So just you're seeing all these identity connections through all these blocks, and they say, okay, let's make it even more complicated. We will provide all this identity connection between all these blocks, add shuffle between each other by cardinality, and get a result. Here we go. So this is how ELAN works under the hood. So all this boring stuff is end. Let math is end as well. Here I will explain how actually this YOLOs works under the hood. Okay, we have actually 7 YOLOs in YOLO v7. So smaller model that's working with edge devices as well as normal GPU. There's a small amount of required flops on your model, but require a little bit modern video card. What does it mean? So basically, all these YOLOs are using a float 16 half precision. It means that if you're using, I don't know, V100 T4 or any others, new video card from NVIDIA, you will get a benefits. But if you're using an old video card, like, I don't know, Key 80, Key 40, or even older, the YOLO v7 will be slower than others and may not provide a good result for your case. And yeah, so here we go. YOLO v7 tiny was simplified from YOLO v7 by removing a few blocks to make it even faster on a particular edge devices. For example, replace a downsampling with max pooling, or even just replace a few blocks completely because it's make it not so comprehensive. But it works so fast that we can apply it for, I don't know, NVIDIA Jetson Nano. So here we go. You heard about a few things, about ELAN or auxiliary head, and if you're working with all this stuff and you were just wondering, everything was applied for every model, but it's not true. Yeah, YOLO v7 ELAN was applied only for the biggest model because it consists the biggest amount of weights, and there is a problem with all this gradient descents, paths of it, and so on and so forth. Whereas tiny model doesn't have enough weights to have this kind of problem. Therefore, no sense to use a ELAN. But reparametrization, putting into chromalization layer, YOLO R modification was applied for all of these models. Therefore, they improved number of weights at 2 times rather than the previous YOLOs. So it became even tinier, even smaller, but at the same time was performance was increased with a half precision. And therefore, if you know there is a battle between Yolo v5 and Alexei and authors and Alexei Bashkarovsky, because Yolo v5 inventor authors didn't present the article and didn't compare with the previous Yolo v4 that was made 6 months earlier than they presented in the GitHub repository. So right now we have a paper with code chart, and it provides that and says that Yolo v7 is the fastest and the best model that we have right now. I mean, for real-time object detection. Of course, there are a lot of models that outperform Yolo v7 in particular cases like object detection, but not in real time. But these models not work in real time actually. Therefore, we wouldn't say about it. We'll say about nothing. Okay, here we go. Battle between Yolo v5 and Yolo v7. You will if you will run your model, for example, your data with Yolo v5 and Yolo v7, you can understand that Yolo v5 is outperform Yolo v7, and you're just wondering why it happened. Okay, here is one thing. If you're working with a different model, you need to compare it fairly. Therefore, it have actually alike methods of measuring metrics. First of all, Yolo v7 was originally tested and trained on half precision, which means if your device doesn't support half precision, performance might be reduced. And if you're just comparing the different models, for example, Yolo v5 and Yolo v7, you need to pay attention how all these metrics was calculated and what kind of assumption has been made. For example, after of Yolo v5, assume that the recall is equal to 1, is always achievable, whereas after of Yolo v7, not. For example, why they don't, for example. Suppose today you are doing an image classification task, and in this case, we can assume that maximum recall is 1, because we always can, decrease the threshold to 1 and detect everything on these images. But it doesn't work for object detection, because if there is a thing like a UI threshold, and if it won't achieve, it won't exceed this threshold, it couldn't be equal to 1, this kind of recall. We just miss a few objects and it wouldn't be, works a lot. Since then, Yolo v7 works better than Yolo v5 for new devices. But if you're working with the old devices, maybe a good idea to work with the Yolo v5 or even Yolo v6 that was presented by, inventors of Yolo v5 as well. Yeah. And a few more things like application of these YOLOs and what we do with all this stuff. Here we go. So with YOLO R head, we can use a multi-task training as well. So here we go with YOLO R provides us a few more things than just object detection. It helps us to print the mask or segmentation task for particular devices, and provide us a few more things like keypoints. We can build keypoints for people, and how it can help us make it understand: did this person fall down on the floor, come to some restricted area, or I don't know, just maybe shaking his hand with somebody else, and it's maybe, I don't know, we should provide him some warning like, hey, you are shaking hand with a positive COVID positive guy, you should pay attention on, try to avoid all the stuff. You should just maybe shake elbows, how they do it in Canada, but yeah, pretty strange anyway. And yeah, we made this kind of model. They made this model. We applied it for our projects, but we need to understand how we can serve all these models. So, and he's come up and treat on inference server. Triton inference server. So you can, build your model. It will be just artifact that you can serve through anything. And I would like to eager you to use Triton inference server as analysis, because if you just would like to use Triton on CPU only, it works well. But if you just would like to move from CPU to GPU, it works even better because it was built by engineers from NVIDIA. And how it works. So your model working in some specific memory that could be called from different threads simultaneously. That's looks impossible for Python developers. What? GIL? No GIL. Therefore, you can apply all the stuff freely. It's works just under the hood. A lot of different examples that help you to push your YOLO models into Triton inference server or any other models, and you can get all these benefits from using a well-developed inference server like metrics, scalability, building an entire pipeline that's the model results flowing from one model to another without moving from GPU to CPU. That could happen in your particular case. And this here I would like to stop and ask you if you have any questions, and I'm happy to answer. Thank you.
Thank you, Rinat. We have one question already. And the question is, which tools and languages do you use to design YOLOs?
Okay, I just would like to emphasize that I didn't design YOLOs, but languages and all these tools. I'm working basically with PyTorch. It's a framework, and is YOLO actually implemented on PyTorch. And for working with PyTorch, we just can, train the model. After article presented a training script as well. But if you would like, you can just write it up with PyTorch Lightning and put it any way you would like. And also, for inference, we're using Triton inference server. Basically, But in the same times, server supported by SageMaker as well, and we just run all the stuff inside of SageMaker. I hope I answered on your question. Thank you.
Okay. I hope you answered as well. Any other questions, guys?
No more questions. Everything is fine.
Yeah, I hope so. All right, so
there was a couple of guys asked me in DM regarding HLL internal implementation. So whenever we finish with Rinat's question, I can also jump and answer that.
Okay, I think you can answer, and maybe meanwhile someone will have another question for Rinat.
Yeah, so HLL is probabilistic data structure, and as an input, it has number of different strings. And the first step in this algorithm is to turn these strings to bit strings. So we have sequences of ones and zeros, and there is a lot of them. But imagine in this long list that we have one single unicorn. And this is a sequence, a very special sequence that has all the leading zeros, so 0, 0, 0, and then only 1. And this unicorn probably exists in a very long list, but also the number of leading zeros probably related to the number of elements in this whole list. And that's kind of the hint that was used from probabilistic theory to calculate number of elements in the whole list based on the leading zeros of this kind of unicorn. So while the first step is to create a bit strings from the initial strings, the second step is to walk through the whole list of these bit strings and find the string that has the longest number of leading zeros, and that the eventual number of elements in the list would be 2 to the power of number of leading zeros, if that makes sense. So there's no some kind of hierarchical structure in there. It's literally just a list of bit strings. And this is speaking about the structure itself. But then whenever we trigger on this HLL, give me the number, it goes through the list and checks the number of leading zeros. I hope that makes sense. Thank you.
Okay, thank you. I don't see any other questions. So I think we can stop at this point. Thank you guys very much. Thank you everyone who attended. In a few days, we will send you an email with the presentations and the recording of this meetup, this webinar. And again, subscribe to our social media not to miss any future meetups. I hope you enjoyed this one. If you have any feedback, suggestions, you can also reply to the follow-up email and we'll be glad to improve it in any way. So thank you guys. Have a nice day or evening or whatever, and hope to see you soon on the next events. Bye.
Thank you. Bye.